Lesson 4.2 has us expanding our horizons, graphing rational functions. A rational function is a function of the form f of x equals n of x divided by d of x, where the top part of the fraction just means the numerator, the bottom part is the denominator. In lesson 4.1, we talked about the parent function being a reciprocal function. Now we're just going to focus on utilizing that numerator and denominator to create a transformation of the parent function. Example 1 on the right. Rewrite g of x equals 4x divided by x minus 3 using long division. So as is, g of x represents a rational function. But to show the transformation, we're going to have to kind of rewrite it, showing the transformation left and right, and the possible transformation up and down. So here's what we do. We're going to start off by doing long division. This will help us determine our quotient and remainder. Since the denominator is x minus 3, that's our divisor in our long division problem. 4x is our polynomial that we put on the inside, or our dividend. If we write 4x on the inside, remember our long division rules. We took the first term on the outside and tried to make it equal the first term on the inside. X to become 4x, what we would do is just multiply it by 4. And then we distribute that to both parts in the divisor. 4 times x is in fact 4x. 4 times negative 3 is negative 12. Now remember, we subtract this row. So if I subtract everything, I'll subtract the 4x, but then I'm going to actually add the 12. 4x minus 4x cancels out, and we have a remainder of 12. It's that quick to show the division. Our quotient would then be 4, that's it, with a remainder of positive 12 over x minus 3. Now that kind of looks like what we graphed in 4.1. So the second thing we'll do is kind of look at that transformation and describe what's going to happen on our graph. We can rewrite g of x. We actually had the remainder portion of the equation written first yesterday, 12 over x minus 3, and then plus 4. When we described this transformation, we said it went 3 to the right and it would go up 4, based on what's happening with the denominator and that plus 4. To sketch the graph, we're going to determine the domain and the range. The domain is based off of the denominator. Since it's x minus 3, we know that the domain will be x can't equal 3. For the range, if x can't equal 3, that means that fraction can't equal 0. And if we add 4, that means g of x won't be able to equal 4. Let's go ahead and draw in our asymptotes based on those rules. We know that we'll have a vertical asymptote at x equals 3 and a horizontal asymptote at y equals 4. Go ahead and draw those two dashed boundary lines in. At this point, our graph should look something like the picture on the right. The last thing we need to do is create some additional points. Now we know by now the typical kind of shape that these graphs should look like. We just need to determine some turning points. What I'm going to do then is use my vertical asymptote as my guide. I'll pick values that are less than 3, and then I'll try to pick some values for x that are greater than 3. If I pick a number less than 3, like 2, I'm going to plug 2 in to my equation and simplify. If I plug in 2 for x, 2 minus 3 is negative 1. 12 divided by negative 1 is negative 12. Negative 12 plus 4 is all the way down to negative 8. Let's pick another number. I'm going to go to 0. If you plug in 0, 0 minus 3 is negative 3. 12 divided by negative 3 is negative 4. Negative 4 plus 4 is 0. Let's go ahead and plot these points. Well, let's pick another point. Let's go all the way over, I don't know, let's say negative 5. Just kind of get an idea of what's happening there. Negative 5 minus 3 is negative 8. 12 divided by negative 8 is negative 1.5. Negative 1.5 plus 4 is 2.5, or I'll say 2.5. I think this should give us a good idea of what our picture looks like. 2 down to negative 8, 0 at 0, negative 5 up 2.5. So you can see it kind of approaching the vertical asymptote pretty quickly at 2, negative 8, and then that horizontal asymptote as it's going through negative 5, 2.5. Go ahead and draw a curve through those values. And hopefully it looks similar to this one. If we pick values that are greater than 3, we'll start with 4. Now what happens when we plug in 4? 4 minus 3 is 1, 12 over 1 is 12, and then if we add 4, it's all the way up to 16. So it's way off of our graph. 4 would be like way up here somewhere. So let's plug in numbers further away from that asymptote to see if we can get values to fit. I'll bump it over to 7. 7, oh, that is a 7. Let's get that to fit in there. Sorry about that. There we go. 7 minus 3 is 4. 12 divided by 4 is 3. 3 plus 4 is 7. At least that fits on our graph. So 7 up 7, kind of in the middle right there. If I go over a little bit more, maybe I'll just bump it over to 8. 8 minus 3 is 5. 12 divided by 5 is 2.4. And if we add 4 to that, we're going to get about 6.4. So you can see as we keep going to the right, the graph is going to drop down and slowly kind of taper towards that horizontal asymptote. Drawing in this curve should show us our rational function, looking like that transformed reciprocal function from 4.1. And now we get to the more complex form of a rational function. I know there are a lot of steps here. Please make sure to take the time to write them down carefully. Now that we may have kind of higher ordered polynomials within the numerator and denominator, the first thing you're going to want to do is factor. You want to factor the numerator and denominator completely. We'll use that information in kind of a unique form to determine domain and range, kind of like what we talked about at the end of 4.1, day 1. From there, kind of like up above, we'll look at any asymptotes. And then we have some new things. We're going to look at finding zeros of the function. We've done zeros for functions before, but what we'll do is we'll take the numerator only, set it equal to 0, and solve for x. Now, a 0 is only on the x-axis, so we're also going to find the y-intercept. And we'll do that by plugging in 0 to the entire equation and simplifying. And then last but not least, we'll use that domain rule, those vertical asymptotes, to make tables and plot some additional points. That's a lot, so we're only going to do a few of these, kind of just to get an idea of what this process is like. Example 2a, sketch the graph of the function f of x equals 2x plus 9 divided by x minus 3. Include the domain, range, asymptotes, x and y intercepts, along with additional points. So these are all known as our key features. And we'll follow all the steps on the left-hand side to get them. Notice the left-hand side didn't say long division, so we don't have to do that part. The first thing we're supposed to do is factor. So if we have f of x equals 2x plus 9 over x minus 3, nothing factors out of the numerator or denominator, which is kind of nice. So there's no factoring involved in this one. From here then, the second thing we want to do is determine our domain and our range. Remember, the domain comes from the denominator. So in this case, our domain is x can't equal 3. Our range is a little unique. If you recall from 4.1, day 1, when you have a polynomial in the numerator and denominator, the range comes from taking the lead term on the top, or the term with the biggest exponent, divided by the lead term on the bottom. So we have a 2x over 1x. That would be 2x over 1x. If we simplify this, the x's actually cancel out to equal 2. And what that number indicates is that f of x can't equal 2. That's how we get the range. So our domain is x can't equal 3. Our range is f of x can't equal 2. Now we'll do our asymptotes. We'll draw in those border lines. And I'm going to do that in orange, I think. So step 3. Our vertical asymptote, I'll just write it as VA, comes from our domain. So that would be x equals 3. And our horizontal asymptote comes from our range, and that will be y equals 2. Let's go ahead and sketch in our vertical and horizontal asymptotes. All right, now that that's done, let's determine our zeros. Now remember, the zeros come only from the numerator. We're going to set 2x plus 9 equal to 0, and then we solve for x. If we move 9 over, we get 2x is equal to negative 9. Dividing both sides by 2, that means x will equal negative 4.5. As an ordered pair, that's negative 4.5, comma 0. That's the x-intercept. So over at negative 4.5, I'm going to put a dot. There's my 0. Step 5, I know there's lots of steps, I'm sorry. Step 5 is the y-intercept, and this should be easy. If we plug in 0 for all the x's, we would get 2 times 0 plus 9 over 0 minus 3. So pretty much everything that's connected to that 0 cancels out. And that gives us 9 over negative 3, which would equal negative 3. That's the y-intercept, 0, comma, negative 3. Now that should make sense. If we look at those two dots, that would make sense that we'll connect them and try to extend towards both the vertical and horizontal asymptotes. All right, step 6. This is the one where we have to do a little bit of detective work. We're going to use that vertical asymptote, x equals 3, pick values that are on the left side and the right side. So we know how to do this now. X is less than 3, and then we'll pick some values where it's greater than 3. The nice thing about the less than 3 is we already have 2 points. We have 0 and negative 3. We have negative 4.5 and 0. So let's just pick one more, maybe somewhere in between those, or maybe a little bit over to the right. I don't know. Let's pick, negative 3, just to see what happens. If we pick negative 3 in the numerator, 2 times negative 3 is negative 6, plus 9 is 3. If we pick negative 3 minus 3, that's negative 6. 3 over negative 6 would be negative 1/2. So if we go to negative 3 down negative 1/2, that seems to make sense. That would curve to the vertical and horizontal asymptote. All right, let's do some work over on the right-hand side. A number greater than 3, if we plug in 4, 2 times 4 is 8, plus 9 is 17. 4 minus 3 is 1, so 17 over 1 is 17. Way too far off of our graph. So let's pick some values that hopefully will fit for us. I'm going to bump it over to positive 6 and see what happens. 2 times 6 is 12, plus 7 is 20, or plus 9 is 21. 6 minus 3 is 3. 21 divided by 3 is 7. That at least fits on our graph, 6, 7. It's way up high. I'm going to bump it over to 10 and see where we're at. If we do 10, 2 times 10 is 20, plus 9, 29. Divided by 10 minus 3 is 7. 29 divided by 7 is about 4.1. So if I go over to 10, up to 4.1. So notice we don't get a lot to work with over on that right-hand side. But let's see what we can do. Try your best to connect a smooth curve through the points that we graphed on our coordinate plane. Make sure to not cross over either of our vertical or horizontal asymptotes. This is the end of the Part 1 video. When you're ready, go ahead and dive into Part 2 and work on the problems on the back.